Hello there. Let's do IP version 6, because at some point we're going to have to leave IP version 4 behind and move to this version. So let's contrast the two against each other. Let's look at IP version 4 and IP version 6. So IP version 4 is a 32 binary bit address. This gives us round about 4.3 billion addresses in total, whereas IP version 6 is a 128 binary bit address. This gives us 340 undecillion addresses, which is a really weird number and very difficult to wrap our heads around. So it is 340 trillion addresses. That is enough addresses that every human being on planet Earth right now could get 4.3 billion V6 addresses each, and not a single address would be reused. And I would still have addresses left over if I were to do such a thing. And the reason why we have to look at this is because IP version 4's address space is pretty much used up. We're just doing a very good job of treading water right now with the current allocation of IPv4 addresses for public routing. Whereas the IPv6 address space is being made available very conservatively, and even if it wasn't, we have plenty of addresses to go with. There are a couple of other differences between IP version 4 and version 6. One of which is that IP version 4 has a very poorly optimized packet header, at least by modern standards. Whereas IP version 6, on the other hand, has a very straightforward and simplified packet header, and a couple of other benefits as well that are a little bit beyond the scope of Network Plus. But let's have a look at the new IP version 6 header. There are some things that are the same as IP version 4. There are some things that have changed, and there are some new things as well. First of all, the version field is in the same spot it was as when we looked at it with IP version 4. Except this time it'll carry the value of 6 to indicate that this is an IPv6 header and an IPv6 packet. The next field is the traffic class. This indicates the class of the traffic, or its priority. This is very similar to the TOS field in IPv4 and is primarily used for quality of service control. After that, we have the flow label. This is a new one. This field was added in IPv6 to differentiate real-time traffic. A flow label and a source IP address together get used to uniquely identify a data flow. Intermediate network appliances, like routers, can effectively differentiate data flows based on this field, giving better control and capability for traffic prioritization. Then we have the payload length. This field indicates basically how big the payload is. We don't have to have a header length this time though, because the network appliance is smart enough to measure that on its own. Then we have the next header field. This field defines the type of the first extension header if there are any that are going to be included. Extension headers are basically optional add-ons that can be pinned onto the end of this existing header, and it's one of the reasons why this is simplified yet more extendable. One of the big advantages that IP version 6's header brings us is that we can add new fields in the future as and when we learn that we need a new field for something. This is unlike IP version 4 where the header was predefined and not extendable, and it's one of the reasons why some of the fields for the IPv4 header seem so weirdly named and then weirdly used compared to their names. After that, we have the hop limit. This field is very much like the TTL field in IPv4 to make sure the packet doesn't live forever on a network. And then we have the source address and the destination address, both of which will obviously be 128 bits long each. Now, one of the things that I think puts people off IP version 6 mostly is the address. It's 128 binary bits long, and we divide it into 8 segments of 16 bits, where we separate each segment with a colon. Now, the big pain point is basically how we write this thing. If we were to try and rewrite the 128 bits in decimal, it wouldn't work out very well, as each of the 8 segments could be a value between 0 and 65,535. So we tend to use hexadecimal instead. It's a much more friendly numbering system. So borrowing the table from the network numbering system video, let's have a look at this. The main part is the binary, and the hexadecimal column. I've just included the decimal column for context. Every hexadecimal value is 4 binary bits. 0000 for 0, 0001 for 1, 0010 for 2, so on and so forth. Now in terms of how we go back and forth between hexadecimal and binary, it's a straightforward substitution system just like we use for MAC addresses. So if we put an IPv6 address here, like 2001, 0db8, 0000, 0000, 0008, 0800, 200C, 417A. We will just do simple substitution. Whenever we see these particular hexadecimal characters, we will substitute in the corresponding 4 binary bit value that each one represents. So let's start out. I'm not going to do the entire address, it'll take forever. The first 2 segments should be enough. So 2 is 0010. 00, no matter how many times you write it, but obviously we want this to be in binary. So we're going to write 4 zeros for that. Hexadecimal 0, same story there. We will do another 4 zeros. Then 1 is 0001. Colon is a colon, that never changes, thankfully. Another 4 zeros. D is 1101. B is 1011. 8 is 1000. Colon, and so on and so forth. If you want, you can try converting the rest of this for yourself on a piece of paper. But speaking of a piece of paper, jotting down this binary and hexadecimal conversion table could be helpful in the Network Plus exam in case you have to deal with a hexadecimal conversion. Although chances are the binary to decimal conversion table would be more useful. Now, one cool thing we have going for us with IPv6 is we have the ability to shorten an IPv6 address. Now, this is quite fortunate for us because we are early on in the adoption cycle for IPv6, which means that if we can shorten the address as far as typing is concerned, it'll make it a little bit easier to work with. Between the address being written in hexadecimal and looking quite lengthy, it can be up to 32 hexadecimal characters. I think a lot of people are put off by that. So there are 2 things that we can do. We can drop leading zeros from a segment within an IPv6 address, and if we have consecutive segments of zeros, we can replace it with a double colon, but we can only do that once. So let's have a look at this. Let's take that address we used just now for the conversion back and forth and play with it. We're going to drop leading zeros. Now first, let's explain what a leading zero is, so we're all on the same page with that. If I take a value like $900, I do not want to be dropping those zeros because those are trailing zeros and they hold value. Put it this way, I don't think you or I need mathematics to turn $900 into $9. I can do that on my own, thank you very much. If I take a value like $901, there's a middle zero there. Again, it also holds value. I don't need mathematics to help me here. I can turn $901 into $91 myself. But if I write a number like that, $009, those zeros have no value. They're just filling a space, but not representing a larger numerical value. So we could drop them because leading zeros hold no value. They're just holding a space. So if we start applying that to our IPv6 address here, those 2 zeros there, they have value. Not going to mess with it. But that 0 is a leading 0. We could drop that and just write db8. Now the cool thing is, when typed into a network appliance or a server or something like that, it will see the second segment only has 3 hexadecimal characters or 12 binary bits. And the appliance will go, well, there should be 4 hex characters or 16 binary bits per segment. So it'll substitute in zeros until the segment is big enough. So we could scratch out that 0. Then the next segment over here is 4 zeros. Whether I write 1 0, 4 zeros, or 4 million zeros, it's still 0. So we can scratch out those first 3. Same for the next segment. The segment after that, 3 zeros and then an 8. Those 3 hold no value, so we can drop them. Next segment is 0800. That one I can drop. Those 2 I'll leave because they do hold value, so we can drop that one. And the next set of zeros is 200C. Those two hold value, so we will leave them. This will result in a much shorter address that looks like this. 2001 DB8 008 800 200C 4178. Much shorter, much more convenient to work with. But we also have that second thing we can do, which is replacing consecutive segments of zeros with a double colon. But remember, we can only do this once. And we have over there 2 consecutive fields of zeros, which we replace with a double colon, resulting in a shorter address. Obviously, the more consecutive fields of zeros we have, the more segments we can drop and replace with the double colon. When typed into a network appliance, it will see that there are less than 8 segments here, and it'll go, there's a double colon. Let me add more zeros until it is big enough. So we have a much shorter address to type in, and the appliance can work backwards to the original address, giving us human beings a bit of a nicer time, and the network appliances actually use their processors to help us out for a change. Okay, maybe I'm being a bit nasty there, they always help us out. But sometimes with address shortening, you might land up in a situation where you get more than one opportunity to use the double colon. So we've got loads of zeros, 12AB, loads of zeros. If I drop leading zeros, that leads me here. So you can see I've got 3 segments of zeros, 12AB, 4 segments of zeros. Now, remember the rule is I can replace consecutive segments of zeros with the double colon, but once only. So that means I can write it either as 00012AB colon colon or colon colon 12AB 0000. Either one is fine as long as I do the double colon once. General best practice though is to try and replace the longest consecutive run of 0 segments with a double colon. But never do it twice. If you try and do it twice, the network appliance cannot work with that because it doesn't know which of the double colons has how many fields of zeros. There could be 2 fields of zeros there and 5 over there, 3 over there, 4 over there, 4 over there, 3 over there, 5 over there, and 2 over there. It cannot tell. So always pick one and drop it and replace with a double colon and leave the other segments of zeros as is. Personally, I'd go with that one. Now another thing that we've got going with IP version 6 is that there is a bit of a change in how the communications can go down. Borrowing from a previous video where we spoke about how IPv4's communications went, we started out with unicasting, where a bunch of devices in a network are able to communicate via IPv4, and a unicast with the word uni implying one is a one-on-one conversation. Then, with multicasting in a network, we are able to target a select group of devices. So, for example, only the blue blocks are being spoken to. Then in IPv4, we also have broadcasts, where in a network, a message gets sent out to everybody and anybody who could receive it. IPv6 is sort of similar, but changes it up a little bit at the end. IPv6 does unicasting, just like IPv4. IPv6 can also do multicasting, just like IPv4. But instead of broadcasting, IPv6 changes it up and does something called an anycast. Now the reason for this is because think about how big an IPv6 network could potentially be. You don't want a message going to everybody. So an anycast is a little bit more efficient for this. With the same set of devices, what happens with an anycast is the message does go out to everybody. However, in the IP header, we are able to identify the service we are looking for. So only the device that can offer the service or the resource we're looking for will reply actually. So think of the anycast as a message going out from the red block saying, hey, anybody who can respond to me for this thing, please do so. And it does. Compared to IPv4's broadcast-based method, everybody receives a broadcast and has to keep processing and processing and processing until they realize, probably somewhere at the transport session or application layers, oh wait, I can't deal with this thing, it's not for me. Whereas at anycast, we can identify down at the IP level, this is useful or not useful for me to look at any further. And if it's not useful, we discard it and carry on with our lives. If I can work with this, I carry on processing, it's useful, and I reply. Then we need to talk about how we turn IPv6 addresses into networks in a similar fashion to IPv4 when it comes to network addresses and host addresses. And this is done with an IPv6 mask, so to speak. The correct name is actually a prefix, and we always write it in cider. I mean, seriously, you do not want to be writing 32 Fs and zeros. It'll drive you crazy. Now, if the IPv6 prefix, or mask if you want to think of it as a mask, is not specified, we always assume a /64 mask, where basically the address is split in two. The bit of the address that is defined by the prefix is called the network prefix, and the bit of the address that's not defined by the mask is called the interface ID. It is very similar to the network address portion and the host address portion of an IPv4 address. Obviously, it's just way bigger. Now, the prefix that's used to divide the address into these two parts could be shorter, resulting in fewer networks and more interface IDs per network, or the network prefix could be longer, resulting in more networks and fewer interface IDs. But if you've reviewed the subnetting videos, you've got the idea. The longer an IPv4 subnet mask gets, the more networks we have, the fewer hosts per network. Same story here with v6. The longer I make the prefix, the fewer interface IDs I have available per network. Now, it is important that you are familiar and recognize some of the important IPv6 network addresses. So let's run through some of them. The first one that's going to be of interest to you is the all zero address, which can be shortened to : : It is called the unspecified v6 address. It is sort of like 0.0.0.0 in an IPv4 network. It's usually used to represent an unspecified default route or default gateway. Then in IPv6, the very first address, : 1, in other words, 31 zeros with a hexadecimal 1 right at the end, is the one and only loopback address in IPv6, similar to the 127 network in IPv4. Kind of funny. In IPv4, we got 4.3 billion addresses, and we waste about 16 million of them to talk to ourselves. In IPv6, we've got 340 trillion addresses, yet we only set aside one address so we can talk to ourselves. We definitely learned our lessons from back in the day, I think. Then we get something called a global unicast address. The global unicast address is a public-like IPv6 address that we can use to communicate with other entities on the internet. The cool thing is, though, we can actually allocate a global unicast address directly to the computer that wants to go online. I don't have to do it on the router and use NAT to go onto the internet with it, which is pretty awesome. And it is 2000::/3. Although when you do get given a global unicast address, chances are the prefix will be a bit longer than /3. Then the 2001:0db8 address with a /32 prefix is used for documentation and examples. Yep, we have a network set aside so that we can use it in course material and training and stuff like that. Now, this is not too unusual because IPv4 actually also had documentation networks. If you go and check out RFC document, let me see, 5737, the 192.020 network, the 198.51.100 network, and the 203.0.113 networks were reserved for us to do documentation. But obviously, as IPv4 started running out of networks, the documentation examples were made publicly available for use on the internet. And if this ever happens to IPv6, the same would probably happen here. Then we get something called a unique or site local address, which is usually going to be FD00:: with a /8 mask. Now, site local means this is an IPv6 address I can use to route within my private network, but I will be going across a router. Whereas if I want to communicate with somebody in the local LAN segment with me, I use a link local unicast address, which will be FE80:: with a /10 mask. IPv6's multicast range is FF00 with a /8 mask, but we also have a special kind of multicast in IPv6 called a link local multicast, where I do multicast still, but only on the local LAN segment with neighboring appliances. And there we're usually using FF02::/ with a /16 mask. So general multicasting is FF00, and then link local on the LAN segment multicasts is FF02. Cool. Now let's use some of these IPv6 networks and prefixes to better understand and get familiar with how these prefixes or IPv6 masks engage and interact with their relative network prefixes. So let's use the 2001 0db8 network as an example here. Because generally, if the mask is a multiple of 16, the mask usually ends on a colon, which makes it a bit easier for us. So let's plot the address out. 2001 0db8 : couple zeros. I can't fit the whole address on the screen without making it super tiny. And we go and substitute in the binary values for all those hexadecimal bits. And we'll end up with that string of binary values. Now the mask, or prefix as it's correctly known, is /32. So let's put that prefix over here. And just like IP version 4, wherever there's a binary 1 in the prefix, it defines the network address or network prefix portion of the IPv6 address. When it becomes zeros, that is now the interface ID, or sort of like the host portion of an IPv4 address. So over here is where the ones stop and the zeros begin, and you can imagine a line going up into the corresponding position of the address. Everything to the left is the network prefix, and everything to the right is the interface ID. Now this means that all of these bits here could flip from zeros to ones, thus turning the hexadecimal values from 0 to F. And we are technically still in the same network. So this means that this documentation example network begins at 2001 0db8 0000 0000 0000, so on and so forth, all zeros, and it will end at 2001 0db8 FFFFF : FFFFF : FFFF, so on and so forth. So there's the start and the end of this v6 network. Neat. Let's look at another one. Let's go for the site local address, FD00:8. It's a nice, interesting one. Alright, so just like before, we're going to go and take the address, FD00:, loads of zeros, loads of zeros. And we're going to work out the binary. Now, cool thing with the multiples of 4, but not necessarily a multiple of 16 network prefixes, is usually the mask will end between hexadecimal characters. Obviously, if it's a multiple of 16, it ends on a colon, but if it's a multiple of 4, like 4, 8, and 12, or 20, 24, 28, it'll end between hex characters, but not necessarily on a colon. So we take the /8 prefix and plot it underneath. And where the ones stop and the zeros begin, we can imagine a line going up there. Everything to the left is the prefix, everything to the right is the interface ID. This means that everything to the right here can turn to binary ones, thus turning into hexadecimal Fs, and we're still in that network. So that means that generally the site local network begins at FD00, with the rest of the address being all zeros, and it goes all the way up to the end of FDFF, with the rest of the address being all hexadecimal Fs. Great stuff. But let's go for one of the tricky ones now. One of the masks that's not a multiple of 16 and not a multiple of 4. Let's go look at the link local unicast range, because that one's a multiple of 10. So that should be quite interesting. So let's take FE80. We take that address and we start plotting it out. FE80: loads of zeros. Rewrite it in binary, becomes a bunch of ones. 1110, 1000, 0000, more zeros. Fantastic. Say the prefix of /10, which looks something like this. As we did earlier, we look to see where the ones end and the zeros begin, and we can draw a line up there. Now, everything to the left of the line, prefix, everything to the right, interface ID. But this time, it's cutting into the middle of a hexadecimal character. So always remember that. Multiple of 16, prefixes on a colon. Multiple of 4, but not 16, prefixes between hex characters. Anything else, it will be ending within one of the hex characters. So we could swap everything from the red line to the right to a binary 1, turning all of those into hexadecimal Fs, but that is going to become B instead of 8. So that means that the link local address is going to be starting at FE80, with the rest of the address being zeros, but it'll be ending at FEBF, because those two zeros became ones. Therefore, 1011 is B in hexadecimal. Makes it a little bit tricky, but I think this is the type of thing that is putting people off of IPv6 because it's not a natural intuitive counting system. But remember what I said in previous videos. Hexadecimal is just a bunch of symbols that represent values between 0 and 15. It's a bit weird for us to look at because we are taught decimal since we're little kids. And every other numbering system looks strange and foreign to us. Now, when it comes to moving to IPv6, we are able to allocate addresses to our clients in ways that are somewhat familiar to us. You can go and statically assign the addresses to your clients if you want to. You probably will do static address assignment, at least on network appliances and maybe some servers. And just like IPv4, we can take advantage of the Dynamic Host Configuration Protocol version 6, or DHCPv6. You might have actually seen with some of your server operating systems that when you enable the DHCP service, it might already have the IPv6 service up and running the moment you install it. But IP version 6 gives us a third option: stateless address auto-configuration, where the network appliance that gets a static address can help out the clients without needing a DHCP server. What happens with stateless address auto-configuration, or SLAC, is the router would be set up with a static IPv6 address preferably, and no DHCP service. And the router will work with the clients to tell them, hey, this is the network prefix I'm using, and you go pick a random interface ID and let me know what it is, and off you go, which is pretty cool. Personally though, I prefer DHCP version 6 because that gives us a lot of control and flexibility, just like it does for IP version 4. Now, when it comes to migrating to IP version 6, we have a couple transition methods we can look at using. And the reason why we have to transition is because IPv4 and IPv6 are not interoperable with each other. In other words, I cannot be using IP version 4 and you using v6 and us communicate. We either both have to use IPv4, or we both have to use IPv6, or we got to rely on a transition method in between us somewhere. Now, one of the first and most widely used is dual stacking. You've probably noticed that when you look at the IP settings of your network card, you will see your IPv4 details, whether you run ipconfig/all in the command prompt, IP address in Linux or ifconfig in Linux, or if you check it through the GUI, you will see that you have IPv6 settings despite the fact you've never used them. Now what's happening is your operating system is running both TCP/IP version 4 and TCP/IP version 6 at the same time. Your computer will attempt always to communicate via IPv6 first, and if there is no IPv6 setup in the network, it will then fail to using IPv4. And we've been doing this since the era of Windows Vista. Yeah, you heard me right. Windows Vista was the first Microsoft operating system to introduce this capability. Believe you me, we've been trying to migrate to IPv6 for ages, and the world is just not taking the bait. Then we could also look at using tunneling. Now, the idea of tunneling is I would run an IPv4 tunnel across IPv4 infrastructure connecting two IPv6 networks together. So maybe as an organization, I want to use IPv6 internally, but my service provider is still running IPv4. Cool. I set up with my internet connected routers at my two locations, IP version 4, and I set up an IPv4 tunnel between them. And then I send my IPv6 traffic through that tunnel. I could also look at doing network address translation 64, which is the NAT service that we can use to convert IPv6 traffic to IPv4 traffic. It used to be known as a translation server or an IPv6 to IPv4 server, where in my network I will use IPv6, and then when it gets sent to that server, which will probably act as a gateway, the server takes the IPv6 payload, the message that we want to transmit, takes it out of the IPv6 packet and puts it in an IPv4 packet to send on to IPv4 infrastructure. This is actually a pretty cool option if you know that the receiving network does not use IPv6, or if you're unsure if the receiving network is using IPv6. It'll probably be safer that you convert your IPv6 communications to IPv4 before releasing it onto the internet. But for Network Plus, that should be enough for you to get comfortable with IPv6. Ideally, I'd love to tell you as much as I could about IPv6 and spend more time with you on it, but for the purposes of preparing you for Network Plus, this is more than adequate. What I would like you to do, though, is do focus on IP version 4, as it is still widely utilized in the world at the moment. And IPv6's migration is going slow, very, very slow, but steady. So it is coming in the future, so do try and get comfortable and familiar with it. And don't let it scare you. It is just a longer address written in hexadecimal, and with a little bit of new names for same concepts. Other than that, though, it's actually not too bad to work with. And I believe that one day, in the future, when IPv4 is retired, there will be a generation of network engineers that will only know IPv6. And the way you and I feel about IPv4 right now is probably how they'll feel about IP version 6. It is what it is. Otherwise, though, I'd like to say thank you for watching. Really appreciate it. And if you have any friends, family members, colleagues, peers, etc. who would also like to learn Network Plus, don't be afraid to share this video with them. Otherwise, though, I'll see you in the next video.